Now I want to discuss another application of the envelope theorem. This is called the Hotelling's lemma. So the Hotelling's lemma concerns about suppliers when they want to maximize their profit. So let me tell you the setup. So the setup. So now you are a supplier, and then you have a supply function. So the supply function of a good is given by y of x1, x2. And then, of course, the x1, x2 are the input. And then you're selling your product at price P. Okay, the price is P. But the input of manufacturing your good come with a cost. So the cost of x1, x2 are called W1 and W2 respectively. Okay, so the total cost equals to W1 times x1 plus W2 times x2. Therefore, to the supplier, the profit function equals to, as usual, the revenue minus the cost. The revenue is just how much you supply times the price that you sell them. So P times y of x1, x2. And then minus the total cost that is given by the expression here. And then in reality, you try to maximize the profit, but subject to the so-called budget constraint. So here we are. So you try to maximize the profit. Sorry, there's a typo, then no y. So all the y are x2, okay? So you try to maximize your profit subject to the budget constraint that is given by W1, x1 plus W2, x2 less than or equal to I. Well, I here is the total budget. So in these optimization problems, there are three parameters. So what are the parameters? Firstly, is the price that you sell your good, so P. Also, the cost of each of the input, so W1 and W2. So note that in this setup, the total budget is fixed. So I is not a parameter, okay? So it's just the setup in the Hotelling's lemma. So these are the parameters. And then for each fixed collection of parameters, then you can find the maximum profit. So the maximum profit is called pi. And then for different sets of parameters that you choose, you will get different maximum profit. So that's why pi depends on P, W1, and W2. So what does the Hotelling's lemma tell you? The Hotelling's lemma tell you what is the rate of change of the maximum profit with respect to the price of your good. It turns out it equals to y evaluated at your maximizer. Okay? So let me give you a proof of the Hotelling's lemma. So proof. So you smell the envelope theorem, right? But to apply the envelope theorem, we have to firstly write down the Lagrangian. So the Lagrangian, in this case, is given by P times y of x1, x2 minus the total cost. And now I've only one inequality constraint, so minus lambda. And then W1, x1 plus W2, x2 minus I. Okay? So this is the Lagrangian. And then we want to study what is the derivative of the maximum profit with respect to P by the envelope theorem. This is the same as taking the partial derivative of the Lagrangian with respect to P and then evaluate at your maximizer. Okay? And then what is dLdP? Well, look at the Lagrangian. Where do I have P? P is here. So when I differentiate P, well, everything else die, and then P become 1. So I get just Y at x1, x2. What's my maximizer? The maximizer is assumed to be x1 star, x2 star. So this x1 star, x2 star. So of course, this is y of x1 star, x2 star. Okay? But what is the implication of the Hotelling's lemma? So interpretations of the Hotelling's lemma. So although the proof looks very simple, but actually it's a very meaningful statement. That is, the rate of change, it states that the rate of change of the maximum profit with respect to P. What is P? P is the price of the good. Turned out to be exactly equals to y, okay, y of x1, x2 star. So that is, what is y? Y is the supply function. So that is the supplied function evaluated at the maximizer. So this is a very interesting fact. So it turns out the rate of change of the maximum profit with respect to how much you sell your good is governed by the maximum supply of your supply function. Okay, so this is the key insight of Hotelling's, and that's the statement of his lemma. So let me put a box here. So I hope that you find the envelope theorem very interesting because it has a very wide range of application in many aspects.